Welcome to the Deep Dive. Today we're looking into something pretty profound, I think. Revolution in AI that's, well, kind of happening quietly. We usually picture AI as these giant cloud servers somewhere far away. But that's changing. AI is moving literally onto the devices we use every single day. We're talking about on-device AI. You might also hear it called edge AI. And what it means is running these pretty sophisticated machine learning models, not in some distant cloud, but right there on your phone, in your car systems, maybe even tiny IoT sensors. It's all about bringing that intelligence closer to the data source and, well, closer to you. So what's really behind this? Why this big shift? Why do we suddenly need AI on the device itself instead of just relying on the cloud? We're going to unpack some really compelling reasons for that, and we'll look at the main toolkit making this happen. TensorFlow Lite, though it's increasingly being called LiteRT now, which is strategically important, as we'll see. So our mission today, to really get under the hood of on-device AI.
What is it? Why should you care? How does this LiteRT thing actually work? And maybe most importantly, how can you actually use this stuff to build cool, intelligent applications? Yeah, get ready to maybe rethink where AI really belongs. So diving into that, why this move away from the cloud, it's a big architectural shift. And from what I've seen, it feels like it rests on maybe 4 key pillars, each one tackling a problem with the old cloud-only way.
Yeah, you've really nailed it there. It's not just, a small improvement. For a lot of applications, on-device AI makes things possible that were just, well, impossible before or totally impractical. Think of these pillars as the fundamental drivers.
Okay, let's start with the first one, latency. That need for basically instant results. With the cloud, you've always got that round trip, right? Data goes up, gets processed, comes back down. Milliseconds, sure, but they add up. But it's more than just annoying lag, isn't it? Where does that cloud latency become a real showstopper? Any surprising examples where on-device just blew it away?
Oh, absolutely. It's about safety sometimes, not just convenience. Think about autonomous driving. Yeah. Or maybe remote surgery using robots. Every single millisecond counts there, critically counts. A cloud round trip, just the physics of it means you can't guarantee that instant response. On-device eliminates that network trip entirely. You get near zero latency, which is, well, essential for real-time mission-critical stuff. It's a complete game changer in responsiveness.
And staying with critical data, that leads nicely into the next pillar. Privacy. We're all much more aware of privacy now, regulations like GDPR. Sending sensitive stuff, images, audio, personal texts to a server, that feels risky, both for users and, frankly, for developers.
It's completely transformative. On-device ML means, by design, that personal data often never leaves the phone or the device it's on. The processing happens right there, locally, so it's inherently more secure. And it makes complying with things like GDPR way, way simpler. It's not just about avoiding fines either. It builds trust. Users feel more confident. It's really a design choice.
Right. Privacy by design. Makes sense. Okay, so beyond privacy, what if you just don't have internet? Connectivity. Cloud AI only works if you're online. That limits things, right? Think rural areas, basements, tunnels, even just spotty city Wi-Fi.
Exactly. On-device AI democratizes access. It completely decouples the smart part from needing a network connection. This offline first thing is incredibly powerful. Suddenly, you can use AI in farming, where broadband is patchy, or environmental sensors deep in a forest, or emergency situations where cell towers might be down. It lets critical apps work reliably, anywhere, anytime.
Okay, pillar number 4, power and cost efficiency. We all know network connections drain phone batteries.
Yeah.
But the cost side of on-device AI, I feel like that's maybe underestimated sometimes.
Oh, definitely. Reducing network chatter saves battery, sure. But think bigger picture, the economics. Running inference locally means you don't need huge, expensive server farms in the cloud processing every single request from millions of devices. That's massive savings on operational costs. It actually makes certain AI features viable that just wouldn't have been affordable otherwise. Imagine deploying AI on millions of really low-cost, maybe even off-grid devices. Suddenly, you can build entirely new kinds of AI services, reach new markets. It fundamentally changes the cost of deploying intelligence.
Okay, so those are some really strong reasons pushing toward on-device. We need the tools then. And for a long time, TensorFlow Lite from Google has been, well, the main player. But you mentioned it's evolving. LiteRT, what is that exactly and why the change?
Right. So LiteRT, or Lite Runtime, is Google's framework specifically built for this, for running models efficiently on devices with limited resources, phones, embedded systems, you name it. The key thing, as you said, is the shift, the rebranding from TensorFlow to LiteRT. It's not just marketing. It really signals a deliberate strategic move to decouple the on-device runtime part from the main TensorFlow training framework.
Ah, okay. That's a subtle but important difference because people probably thought T-Flight was only for models you trained using TensorFlow itself.
Yeah.
So what does this decoupling mean if I'm, say, a developer who prefers using PyTorch or JAX for training my models?
It basically means freedom. The official LitR documentation is now very clear. Its conversion tools aren't just for TensorFlow models anymore. They explicitly support converting models from PyTorch and JAX, too. This really positions the .tflight file format, that's the output of the conversion, as this universal, optimized, portable format specifically for the edge. Almost like Google's answer to ONNX, maybe, but with their whole ecosystem behind it. So for you as a developer, learning LitR isn't just a TensorFlow skill now. It's becoming a core on-device AI skill that you can use regardless of how you trained your model. That's a huge deal for making edge AI more accessible.
That makes a lot of sense. It opens things up.
Ah.
Okay, so strategy aside, let's get into the nuts and bolts. How does LitRT actually work? What are the key pieces inside?
Well, fundamentally, there are two main components you interact with. First, there's the TensorFlow Lite converter. Think of this as a Python tool. It's the bridge. It takes your big, complex, high-precision trained model and transforms it. It makes it smaller, optimizes it, often using techniques like quantization, which we'll definitely get into later, and spits out that artifact ready for the device. Then second, you have the TensorFlow Lite interpreter. This is the actual engine that runs on the edge device. It's designed to be super lightweight, minimal memory use, fast to start up, all crucial for devices without much power or memory. It takes that converted.tflight file, loads it, sets up the memory it needs, and gives you the API to actually run inference to make predictions.
Okay, so converter prepares it, interpreter runs it. Makes sense.
Yeah.
So an application using LitRT, it follows a pretty clear path then.
Yeah.
From training all the way to running live.
Yeah, it's generally a four-stage workflow. First, you train your model, usually on a powerful machine, probably with GPUs, using whatever framework you like, TensorFlow, PyTorch, JAX. Second, you convert it. You feed that trained model into the LitRT converter. It applies optimizations, generates that .tflight file. Third, you deploy it. That means copying that small .tflight file onto your actual target device, like a Raspberry Pi, or into your mobile app bundle. And fourth, you infer. The LitRT interpreter on the device loads that file and uses it to make predictions on new data coming in, maybe from a camera or a microphone.
And that .tflight file format you mentioned, what's special about it? Why is it so good for the edge? Is it just like a zipped version of the model?
No, it's much cleverer than that. It uses something called flat buffers. It's not just the model weights, it's the whole model structure represented in this format. And the cool thing about flat buffers is you can access the data directly in place without needing to parse or unpack it first like you do with JSON or protocol buffers. For an edge device, this is huge. The interpreter can basically memory map the model file and start running it almost instantly. Minimal delay, minimal memory overhead. It's built for speed.
Gotcha. That makes sense. Now, before we get hands-on, one quick clarification. Within this T-Flight world, there are actually two main versions, right? We're focusing on LitR, but there's also something for microcontrollers.
Yes, good point. That's important to distinguish. LitRBite, our focus, is for more capable edge devices. Think smartphones, Raspberry Pis, embedded Linux systems, devices with, megabytes or gigabytes of RAM, a proper operating system. Then there's TensorFlow Lite for microcontrollers, or TFLM. That's a whole different beast designed for extremely tiny devices. Microcontrollers with maybe only kilobytes of memory, often no operating system at all, like an ESP32 or an ARM Cortex-M chip. The engineering challenges are quite different there. So yeah, today we are squarely focused on LitRBite for these more powerful, real-time capable edge devices.
Perfect clarity. Okay, let's get practical. The core workflow, that first step, converting a trained model to .tflight. If someone's just starting, what's a good model to try, and what does that conversion process generally look like in Python?
Yeah, a great place to start for vision tasks on the edge is something like MobileNet v2. You can grab a pre-trained version easily from, say, tf.keras.applications. It's already designed for efficiency. The tool you'll use is the tf.lite.tflight converter in Python. The basic flow is .load your trained model, maybe a Keras model, create an instance of this converter pointing to your model, call the convert method, and then save the result to a .tflight file. It makes a complex process seem pretty straightforward.
Okay, but I remember you stressing something earlier, the importance of starting with a Float3D2 baseline before you start trying all the fancy optimizations. Why is that step so critical? Feels like a common mistake to skip it.
It is a very common mistake, and it causes so much pain later. It's really about methodical debugging. Look, you could jump straight to trying full integer quantization, the most aggressive optimization, but what if the conversion fails? Or the model runs but gives garbage results. You don't know why. Was it a problem with an operation in your model that LiteRT doesn't support? Or was it the quantization process itself that failed or messed up the accuracy? By first converting to a standard non-quantized float32.tflight model and checking that works, you establish a baseline, a sanity check. If float32 runs correctly but your later quantized version doesn't, boom, you've isolated the problem to the quantization step. It just makes troubleshooting so much easier. It's disciplined, professional workflow.
Right, isolate the variables. Okay, so you've got your baseline.tflight file. Now you want to actually run it on your edge device, maybe a Raspberry Pi using Python. You mentioned a special package for that.
Exactly. You don't want to install the entire huge TensorFlow library on your tiny Pi. Instead, you use the tflight untime package. It's stripped down, containing only the LiteRT interpreter and what it needs for run. Much smaller, much leaner. Perfect for deployment. And the steps to run inference using it are pretty consistent across different models. You load the .tflight model into the interpreter, you allocate memory for the model's tensors, you get details about the input and output shapes, you pre-process your input data, maybe resize an image, normalize pixel values, you set the input tensor with your prepared data, you call interpreter.invoke to run the model, and finally you get the output tensor containing the predictions. It's a standard sequence.
Load, allocate, prep input, set input, invoke, get output. Got it.
Yeah.
So now we've converted a float model, run it, got a baseline. We're ready for the really interesting part. Optimization, making it faster, smaller, more efficient. This is where the real edge engineering comes in, right?
Absolutely. This is where you make it truly practical for the device.
And when you talk optimization for LiteRT, the first word that always comes up is quantization. You said it's maybe the single biggest lever we can pull. Can you break down what it actually is and why it has such a huge impact?
Yeah, it's fundamental. Quantization, at its core, is about reducing the numerical precision used by the model. Typically, models are trained using 32-bit floating point numbers, high precision. Quantization converts these numbers, mainly the model's weights and sometimes the activations between layers, into lower precision formats. Most commonly, 8-bit signed integers, and the benefits are twofold, and they're significant. 1. Model size. An int8 value takes only a quarter of the memory of a float32. So right away, your model file size shrinks by about 4x. Huge for devices with limited storage or for downloading updates over the air. 2. Latency, speed. Many processors found in edge devices, ARM CPUs, specialized AI chips, are much, much faster at doing calculations with integers than with floating point numbers. So if you can convert your entire model to run using only integer math, it runs significantly faster and usually uses less power too.
Okay, 4x smaller and potentially much faster. Sounds amazing. What are the main ways developers actually do this quantization? Are there different flavors?
There are two main families of techniques. The first is post-training quantization, or PTQ. This is a simpler approach. You take your already trained float32 model and apply quantization after training without needing to retrain anything. The most basic form of PTQ is called dynamic range quantization. Here, only the weights are converted to any 8. The activations still flow through the model as floats. You get the 4x size reduction, but the speed gains are limited because the math is still mostly float, and there's some overhead converting weights back and forth. It's easy, just flip a switch in the converter. Optimize.default. For the biggest speed up with PTQ, you want full integer quantization. This aims to convert both weights and activations to int8. This allows the entire model execution to happen using fast integer arithmetic. The catch: to figure out how to map the floating point activation values to int8, the converter needs to see the typical range of values those activations take. So you have to provide a small representative data set, maybe 100, 500 examples of typical input data, unlabeled is fine. The converter runs inference on these samples just to observe and calibrate those activation ranges.
Okay, so PTQ is done after training. But you mentioned it can sometimes hurt accuracy.
Exactly. Squeezing everything down to 8 bits isn't always lossless. Sometimes, especially with full integer PTQ, you might see a noticeable drop in your model's accuracy compared to the original float32 version. If that accuracy drop is unacceptable for your application, that's when you turn to the second main approach, quantization-aware training, or QAT. QAT tackles the accuracy problem head-on. Instead of quantizing after the fact, it simulates the effects of quantization during the training process itself or during a fine-tuning phase. You use tools like the TensorFlow Model Optimization Toolkit, TFMOT, to insert special fake quantization operations into your model graph during training. These mimic the rounding and clamping that will happen in the 8-bit integer world. The beauty of this is the model learns to adapt. Its weights adjust during training to become more robust to the noise introduced by quantization. So when you finally convert the QAT trained model, you often get accuracy very, very close to the original Float 32 model, but with all the speed and size benefits of integer execution.
So QAT gives you the best of both worlds, speed and accuracy. But I guess the trade-off is complexity. You have to actually modify your training process.
Precisely. QAT requires more effort. You need to integrate the TFMOT tools, set up the fake quantization nodes, and run a training or fine-tuning process. With PTQ, especially dynamic range, it's often just one line of code during conversion. So the choice depends on your needs. PTQ is easier, but might impact accuracy. QAT preserves accuracy much better, but requires more work upfront during training. It's a classic engineering trade-off.
Okay, that makes the quantization landscape much clearer. Beyond squeezing the numbers with quantization, what other tricks does LiteRT have for speeding things up on the device? I've heard the term delegates used a lot.
Yes, delegates are the key to unlocking hardware acceleration. Think of them as plugins for the LiteRT interpreter. When you enable a delegate, it looks at the operations in your model's graph. If it finds operations that can be run faster on specialized hardware available on the device, like a GPU or a digital signal processor, DSP, or a dedicated neural processing unit, NPU, it offloads those specific parts of the computation to that hardware. The rest might still run on the CPU, but the heavy lifting gets accelerated.
So it's about using the best processor for each part of the job. What about the CPU itself, though? Is there a delegate just for making the CPU run faster?
There is, and it's actually crucial. It's the XNNPACK delegate. In fact, modern versions of LiteRT usually have XNNPACK enabled by default when running on the CPU. XNNPACK is a library that's super optimized for running neural networks efficiently on standard ARM and by 86 CPUs. It uses all sorts of low-level tricks, like fusing multiple operations together and using advanced CPU instruction sets like Neon on ARM chips. And here's a really important point, something that surprises people. Often, a well-quantized model running on the CPU using XNNPACK can actually be faster and more power efficient than trying to run the equivalent Float 32 model on the device's GPU.
Wait, really? Faster on the CPU than the GPU? That goes against everything we usually hear. Why would that happen?
It's because using a GPU isn't free. There's overhead. To run something on the GPU, you have to copy the data from the CPU's main memory over to the GPU's memory. Then you have to tell the GPU which computation to run, launching the kernel. Then the CPU might have to wait for the GPU to finish and copy the results back. For really massive parallel computations, the GPU's speed makes up for that overhead. But for smaller models or parts of models, that communication and synchronization overhead can actually take longer than just doing the math directly on the CPU with something highly optimized, like XNNPACK. XNNPACK works on data that's already right there in main memory, no expensive copying back and forth. So the critical lesson is, don't just assume the GPU delegate will be faster. You must benchmark. Test it with your specific model on your target hardware. Prove that the delegate provides a net win. Sometimes, optimized CPU is the way to go.
That's a fantastic insight. Benchmark, don't assume. Okay, and for developers targeting Android specifically, there's one more important delegate, right? The NNAPI delegate.
Yes, the NNAPI delegate, Neural Networks API. This is specific to Android. It's a really neat abstraction layer provided by the Android OS itself. As an app developer, you don't target a specific GPU or DSP directly. You just tell the interpreter to use the NNAPI delegate. NNAPI then looks at the actual hardware available on that specific phone and figures out the best way to accelerate the model, using vendor-provided drivers for the GPU, DSP, NPU, whatever is available and most suitable. The big advantage is future-proofing. Your app code doesn't need to change, but as new phones come out with better, faster AI accelerators, your app automatically benefits just by using NNAPI. It's very powerful for the diverse Android ecosystem. We won't use it on the Pi, but it's key for mobile.
Brilliant. Okay. Theory covered, tools understood. Let's bring it all home. We're going to talk through a capstone project, building real-time object detection live from a camera on a Raspberry Pi. This feels like the perfect way to tie everything together. What model are we thinking for this?
Yeah, this is a classic but really effective edge AI task. We'll use a model called SSD MobileNet V2 FPN Lite 320 by 320. You can find it on TensorFlow Hub. It's specifically designed to be efficient on mobile and edge devices, giving a good balance between detecting objects accurately and running fast enough for real-time video.
Okay, SSD MobileNet on the Pi. How do we even start? What's the setup on the Pi itself? Phase 1.
Right, phase 1 is getting the Raspberry Pi ready. Standard stuff first. Update your system packages. Apt update, apt upgrade. Then make sure you have Python 3 and pip installed. You'll definitely need OpenCV pip install opencv-python for grabbing frames from the camera and drawing on them, and numpy, pip install numpy for numerical operations. And crucially, you need to install that try runtime package we talked about. The tricky part here is finding the right precompiled wheel file, .ahl, that matches your Pi's operating system, 32-bit versus a 64-bit, which is ARM version, and your Python version. You might need to hunt a bit on the TensorFlow website or community forums to find the correct one. Getting that right is key.
Got it. Environment setup first. Then phase 2 is prepping the model itself. You said we should probably do this on a more powerful computer, and quantization is key here.
Exactly. Phase 2 is model preparation, best done on your laptop or desktop. You'll download the SSD MobileNet V2 model from TensorFlow Hub, and here's where the optimization comes in. You'll convert it to a full integer quantized int8.tflight model. This is absolutely essential if you want real-time speed on the Pi CPU. Remember, full integer PTQ needs that representative dataset. For an object detection model trained on Quizzico, you'd typically download a small subset of the Quizzico validation images, like Val 2017, and write a little Python generator function to feed maybe 100 or so of those images to the converter during the quantization process for calibration. You set the converter options for optimization, point it to your representative data generator, specify you want int8 inputs and outputs, and run the conversion. You'll end up with your optimized SSD MobileNet V2 int8.tsnickly flight file, and you'll also need a labelmap.txt file that lists the names of the objects the model can detect, like person, car, dog. Then you just copy those two files, the .tflight model and the label map, over to your Raspberry Pi.
Okay, optimized model and labels are on the Pi. Now for the main event. Phase 3 and 4, the actual Python script that runs the detection. What did that look like?
This is the core application logic, maybe in a file called detectrealtime.py on the Pi. Inside that script, you'll first load the label map so you know what the detected class IDs mean. Then you load your SSD MobileNet V2 int8.tflight model using the tflight interpreter and allocate tensors. Next, you initialize the camera using OpenCV, cv2.video capture 0. Then you enter the main loop, which runs continuously inside the loop. 1. Read a frame from the camera. 2. Pre-process the frame. Convert color, OpenCV usually reads BGR, model needs RGB. Resize it to the model's expected input size, like 320 by 320, had an extra dimension because the model expects a batch of images, even if it's just one. 3. Set the input tensor of the interpreter with this pre-processed frame. 4. Run inference.interpreter.invoke. 5. Get the results. The interpreter's output tensors will contain arrays of bounding boxes, class IDs, and confidence scores for all detected objects. 6. Post-process. Loop through the detections. Filter out ones below a certain confidence threshold, say 50%. Convert the relative bounding box coordinates, usually 0.0 to 1 pointer, into actual pixel coordinates for the original frame size. Look up the class name using the ID and the label map. 7. Draw on the frame. Use OpenCV functions to draw rectangles around the detected objects, add labels with the class name and confidence score, maybe calculate and display the current frames per second, FPS2. 8. Display the frame. Use cv2.imshow to show the annotated video feed. Add a check for a key press, like Q, to exit the loop. And finally, after the loop, make sure to release the camera resources. That's the whole end-to-end flow.
Wow, okay. That's a complete pipeline. Read, pre-process, infer, post-process, display, repeat. So we've built it, it's running, we see boxes on the screen, but how well is it running? How fast? This is where benchmarking comes in, right? Why is that so important?
Absolute critical. Just seeing it run isn't enough for an engineer. You need numbers. You need to quantify the performance. So you typically write a separate, simpler script, maybe benchmark.p. Its only job is to measure inference latency accurately. It would load the same .tflight model. Instead of using the camera, it would probably create a static input tensor, maybe just random data of the correct shape and type, like U and 8. Then it would run interpreter.invoke in a loop, maybe 50 or 100 times, measuring the time taken for just the invoke call each time. You do multiple runs to get a stable average, ignoring the very first inference, which might be slower due to initialization. This script can also be used to experiment with things like the number of CPU threads the interpreter uses, interpreter.setnumthreads for Pi45, for example. Finally, it calculates and prints the average inference time in milliseconds and maybe converts that to an average FPS.
Okay, a dedicated benchmark script. And when you run that, comparing maybe the INT8 model we just built versus the Float32 version, or trying one thread versus 4 threads, what results should we expect to see? What does this analysis tell us?
You should see some really clear patterns emerge. First, quantization is king, just like we discussed. The SSD MobileNet V2 int8.tflight model will be dramatically faster, lower latency, higher FPS than a Float32 version run on the same Pi CPU, We're talking maybe 3x, 5x, even 10x faster sometimes. That's the power of efficient integer math on those ARM cores. Second, multi-threading matters. When you run the INT8 model with, say, 4 threads on a Raspberry Pi 4 or 5, which have 4 cores, you'll almost certainly see a significant performance boost compared to running it on just one thread. The LiteRT interpreter with XNNPACK is good at parallelizing the work across the available CPU cores. Now, you probably won't get a perfect 4x speedup from 1 to 4 threads because there's always some coordination overhead, and some parts of the model might not parallelize perfectly, but the improvement should be substantial. Seeing these results, measuring them, and understanding why they happen, integer math efficiency, multi-core utilization, that's the capstone level analysis. It confirms your optimization strategies worked.
That's fantastic. From understanding the why of on-device AI, through the tools like LiteRT and optimization like quantization, all the way to building and scientifically measuring a real-world project, that's quite the journey we've covered. So just to recap for everyone listening, you've really gained a solid foundation now. You understand why on-device ML is becoming so crucial: latency, privacy, connectivity, cost. You're familiar with the LiteRT Converter and Interpreter. You know how to convert models. You grasped the vital concept of quantization, the difference between PTQ and QAT, the trade-offs. You know about delegates for hardware acceleration like XNNPACK and GPU, and crucially, the need to benchmark them. And you've walked through building and analyzing a non-trivial capstone project, which is huge.
Definitely. And the learning doesn't stop here, of course. The field is moving fast. If you want to go deeper, you could explore things like custom operators. That's where you might need to implement a specific operation from your model in C++ if LiteRT doesn't support it out of the box. That's pretty advanced stuff. Or there's the whole emerging area of on-device training. Not training huge models from scratch on your phone, but rather fine-tuning an existing model using local data. This is super important for personalization and for privacy-preserving techniques like federated learning. It's a really exciting frontier.
Absolutely. Look, the skills you've explored today, understanding and implementing on-device AI, they are seriously in demand right now across so many areas. You really are equipped now to think about and tackle a whole range of edge ML problems. So maybe the final thought to leave you with is, where else could you apply this? What about real-time pose estimation for interactive fitness apps? Or maybe ultra-low power audio classification for custom keyword spotting on smart devices? Perhaps novel gesture controls? The edge isn't just some abstract concept anymore, it's a real platform. And now, it's yours to build on.